So let's have example 15. The typical school building floor plan has a reinforced concrete floor of thickness 150 mm. Using the dimensions given in the figure, determine the unfactored loads to be supported by column C2. So C sub column C2 is this one, and column A3, which is this, and the loads on exterior beam and interior beam. So these are the beams. The vertical members are beams. The horizontal members are girders for this case because the beam are framed into the girder. So this is also a beam, although this beam is framed into directly to the columns. And number 3, the exterior girder and interior girder. So loadings for the exterior girder and interior girder. Assume that the beams are, by the way, these are the exterior beams, interiors in between, exterior girders, exterior girders. We have interior girders. Assume that the floor, assume that the beams are pin connected to the columns, so we have simple supports. Further, assume that the floor beams that frame into the columns transfer their loads directly into the columns. So for instance, this beam here, these beams are framed into the column, so the load or the reaction at the ends of these exterior beams will be directly transmitted to the column. Whereas for this interior beam here, this interior beam is, or these two interior beams here are framed into the girder. So therefore, the loads are transmitted to the girder first before the reaction here will be transmitted to the columns. The live loads, the live load to be used for school building is 1.9 kilopascals, and all beams are steel using W310 by 52 in SI. Then this is the equivalent in English system, W12 by 35. The area, the depth, the moment of inertia. And all girders are W410 by 100, which is in English system W16 by 67. So this is the area, this is the depth of the girders, all girders, and this is the moment of inertia with respect to the x-axis, the strong axis. Assume that the live loads are not reducible, so we will not reduce it just like before, and all calculations for the loads of columns must be based on the transmitted loads from the beams and girders. So for instance, the force or load in this column here will be computed based on the reaction of this external girder, these are two identical, and this interior beam here. So we have reaction here. So remember, this is the plan or top view, and for this interior beam here, there will be reactions at the ends, depending on the load. Compute the maximum moment in each beam and girder mentioned above by the equivalent loads formulas. These are applicable when we have a two-way load distribution, but if it is one-way load distribution, we can easily compute the maximum moment based on WL square over 8 formula for simple beams loaded with uniform load. So consider two cases. One, letter A is S is 3.5 and letter B S is 5.4. For letter A, we have to evaluate L over S. By the way, the area of the beam is 10.3 times 25.4 square. 1 inch is 25.4 mm, so the conversion factor is 25.4. And it is 6645 mm square. Area of the girder is 19.7 times 25.4 quantity square, so 12,710 mm square. The depth of the beam is 12.5 times 25.4, 317.5, and that of the girder 16.3 times 25.4, 414 mm. Then for part A, L over S is 9 over 3.5. That's greater than 2. So we have a one-way distribution, meaning to say the tributary area would be rectangular. So this is the tributary area for the interior beam. This is also an interior beam. We have the same tributary area, interior beam, interior beam, interior beam, interior beam. But for the exterior beam, the tributary area will be half of that for interior beams. So weight of concrete floor is specific weight 2.4 times 9.31. It's not given here. So times cross-sectional area of the end. So if you look at the end here, end view, this length is S, which is 3.5, and the thickness of that floor is 0.15, 150 mm. So the uniform weight of the floor, concrete floor, is 12, reinforced concrete floor is 12.36 kilonewton per meter. Then the weight of the beam is specific weight 7.86, 9.81. The cross-sectional area for beam is 6645 divided by 1000 square to make it meter square. So that WB is in kilonewton per meter. We have 0.5124 kilonewton per meter. For the girder, it is 7.86, 9.81 times 12,710 over 1000 square. So the uniform weight of the girder is 0.98 kilonewton per meter. So the total uniform load on the interior beam therefore is equal to 12.36 kilonewton per meter plus the weight of the beam. Take note, this is the weight of the beam. Then plus live load 1.9 kilopascals, multiply that by S to make it kilonewton per meter. So the total uniform load in the beam, interior beam is 19.52 kilonewton per meter. Then that's for interior beams. There are so many interior beams there. For the exterior beam, we have W total for the exterior beam is 12.36 over 2. We divide it by 2 because S, the length of this is S over 2. So 3.5 over 2 is 1.75. So in other words, 12.36 divided by 2. Plus the weight of the beam, which is 0.5124, plus the live load, which is 1.9. We just multiply it by S over 2, which is 1.75. So the total uniform weight over the exterior beam is 10.02 kilonewton per meter. Now, if this is the loading distribution, then for the exterior exterior girder rather, the loading would be the weight, uniform weight of the girder and the reaction at the end of the interior beam for that beam. For the interior girder, the loading would be the weight of the girder plus the reaction at the end of the beam. And since there are two interior beams, you have to multiply it by 2. Then for the exterior beam, there's no problem because this is the uniform load. And we have the weight of the beam, which is already incorporated in the problem. So likewise, we have to convert moment of inertia for the beam with respect to the strong axis, which is the x-axis. So 285 times 25.4 raised to 4 is equal to 180.626 times 10 to the 6 and n to the 4th. For the girder, it is 954 times 25.4 times raised to 4. So it is 397.085 times 10 to the 6 and n to the 4th. So this is the tributary area for this column C2 here. And for tributary area for column A3 would be that. Okay, so we will show this on the. So if we consider the exterior girder, for the exterior girder, as mentioned earlier, the loading of the exterior girder would be the weight of the girder itself plus the reaction at the interior beam. So we call that R interior beam. So for R interior beam, it is W of the interior beam times length of the interior beam, which is 9 divided by 2. Or in other words, WL over 2. So the uniform weight of the external girder would be the weight of the girder itself, and the R interior beam is W of the interior beam, which is computed in the preceding slide, 19.52 times L over 2. So R interior beam is reaction in the interior beam is 87.84. Therefore, the loads on the exterior girder would be 0.98 kilonewton per meter, and we have a concentrated load at the center. By the way, the length of the girder is 7 meters. 7 meters is 3.5 times 2 because we have only two spaces for the exterior girder. So the loads on the exterior girder would be 0.98 kilonewton per meter, and we have a concentrated load at the center of the girder, exterior girder, which is equal to 87.84 kilonewton at the center. For the value of the reaction in the exterior girder, which will be transmitted to a column, it is 1/2 of the uniform weight times L over 2, so 0.98 times L over 2, and this concentrated load, which is R for the internal beam, is also divided by 2 to be transmitted here and here. So 87.84 divided by 2. So R, or the reaction in the exterior girder, would be 47.35 kilonewtons. Loads on the interior girder would be uniform weight of the girder. Then, because this is interior girder, then we have to double this R interior beam. So weight on uniform weight of the interior girder, and we have a concentrated load at the center, which is double this value. So 175.68 kilonewton at the center. So if this is the interior girder, this is the uniform load 0.98, then we have 2 times R sub internal beam. Okay, so that is equal to 175.68 kilonewton. So we now compute the force or load on column C2. But before that, let's solve for the reaction of the interior girder. We have half of 0.98 times L over times L, one half of 0.98 or 0.98 times 7 divided by 2, plus half of 2R internal. So half of 2 times R internal beam is R internal beam, which is 87.84. Then the reaction here would be 91.27 kilonewtons. So let's now isolate the column and the tributary area. So this is column 2. At the left side, here and here, the reaction is equal to the reaction of the exterior girder. Since we already computed the reaction of the exterior girder, which is equal to 47.35, so that means the reaction here is 47.35 directly transmitted to the column because this girder is framed into the column directly. On the other side, it's also 47.35 by symmetry. You look at the original figure so that you can analyze. Then here, this is the interior beam. So the reaction at the end of the interior beam is equal to the reaction at the interior beam, which is 87.84. So therefore, the total load on column 2 can now be computed. It is equal to 2 times 47.35 plus 87.84. How about for column? So that's a tributary area. Dimensions 4.5, half of 9, and this is 7 because this is S over 2. And that, sorry, this is S, and that is also S, so 7 for that column. So this is for the column A3. So column A3. So we have here, this is an exterior beam. So the reaction at the exterior beam is, the load is 10.02 times 9 divided by 2. So 10.02 times 9 divided by 2, that's 45.09. This is an exterior girder, so the reaction here is equal to 47.35. So the load for column A3 would be the sum of these two loads or two reactions. So this is the tributary area for column A3, and half of L is 4.5. This is just S because the distance of the next column is also, the distance between two columns is 2S. So that's why half is 3.5, just S. So the force on the column C2 is equal to 2 times 47.35 plus 87.84. So that's the force transmitted to column 2, C2, 182.84 kilonewtons. Then for this column A3, or the other way is pressure on this slab. The pressure is 2.4 times 9.1. The specific weight of concrete times the thickness is 0.15, so that would be in kilopascals. Then this is the live load in kilopascals. Those live loads in kilopascals, or total pressure, we multiply that by the area of the diagram. So, but before that, let's just compute the pressure over this area first, 5.4316 kilopascals. And take note that there is a beam here, and this beam is common to this area and to the next beam. Same is to here. So that F of column C2 by means of tributary area is 5.4316 times the area, which is 7 times 4.5, plus we have a beam which is half beam. Then we have half of half beam because the other half would be, remember there is a beam here, but the weight of the beam is not, half of this weight of beam is not distributed to this, but also the other half would be there. Then this is half a beam also. The half is distributed here, the other half is distributed there. So in other words, the total length of the beam is, this is 4.5, and this is, since this is only half of the beam and the other half must be distributed here, so this is supposedly weight, half of the weight of beam of length 4.5, half of weight of beam which is length of 4.5. So if you add the two, that becomes one whole beam of length 4.5. So it's just like there are two beams of length 4.5. So two beams with length 4.5, that makes it 9 meters length. So 0.5124, the weight, uniform weight of beam times 9 meters. So the force then plus 0.98 times 7, which is the weight, uniform weight of the girder, and the total length of the girder is 7. So this weight of girder will be also transmitted to column 2. So it will give us the same answer, more or less. So the small discrepancy is because of rounding off values, especially for pressure, for uniform weight of beam, and so on. Then R of exterior beam is uniform weight of over the exterior beam, and length divided by 2. So that's the reaction. That's why you get 45.09. This 45.09 is actually, this is the calculations. So F of column A3 therefore is 45.09 plus 47.35 here, this side. So the force on column A3 would be 92.44 kilonewtons. So the other calculation by means of pressure, the pressure here is 5.4316. We already computed that, times the area, which is 4.5 times 3.5, plus the weight of, this is a girder, This is a beam, and take note there is also beam here. There is also beam here. So weight of beam times 0.5124, 0.5124 weight of beam times 4.5 plus half of the weight of the beam. So 0.5124 times 4.5 divided by 2, because the other half will be distributed to the next beam here. So this is one whole beam, but the other half would be transmitted to this column. The other half would be transmitted to the column A2. We have column A2 here. So the other solution is, it is 5.4316, the pressure of times the area, which is 3.5 times 4.5, plus weight of beam, which is this beam here, 0.512, for the length is 4.5. We also have a beam here, which is to be divided into 2, because half would be transmitted to A3, half would be transmitted to A2, column A2. So plus 0.5124 over 2 times 4.5. I hope you got the idea. You look at the original figure so that you can analyze it well. Then plus the weight of the girder. This is a girder and the length is 3.5, so 0.98 uniform weight of girder times 3.5. So computing for that value, it is equal to 92.44, which is equal to that. So that's it on how to compute for the loads and for the force transmitted to the columns. And there, for the force transmitted to the columns, we solved it into two ways. One is based on the reactions at the interior beams or exterior beams, and reactions for reactions at the ends of the exterior girder, at the ends of the exterior girder. And the other one is based on the pressure and the weight. If you look at the figure on top, the weight of the girders and beams attached to that column. So that's the idea.